All right. Um, Hi, everyone. My name is Leslie Wubble. I am the CEO of Open Vessel. We are a startup in regards to open source, and our main goal is really bringing AI closer to medicine. We really aim to provide professionals with quality testing in regards to AI. They start in a research setting, and they really need a lot of development to bring them into a clinical application. And one of our main core values is that we're open source. That means that we're transparent, our code is audited, we can validate models better, and we can develop at a lower cost. What we've done so far is that we started in February of 2020, and we competed in the NITNI AI competition, over the course of which we interviewed 33 radiologists about your problems and your workflow and what you guys deal with on a daily basis. We've also collaborated with Dr. Patak from the University of Maryland. He's kind of educated us on your world a lot. And really, what made us win the competition was an unsupervised algorithm known as k-means, which I'll explain later on in the presentation. Where are we going? So basically, we identified that there's an education gap between data scientists and the medicine field. And basically, what that means is that data scientists and computer scientists aren't really aware of like what is DICOM, what is HL7, what does a system look like in a medical scenario, like how's data moving and stuff like that. So it's really that frontline exposure is what's needed to really learn what we need to do to give you, the best technology there can be. And it's our second goal is to develop skills for deep learning. And we've kind of played around a lot with machine learning. The next step to AI is really deep learning with CNNs or convolutional neural networks. Our third goal is the end goal is clinical implementation of AI, and that is really the core success to getting AI to impact patients' lives. You probably heard of ChexNet, which was ammonia detection developed by Stanford, where they compared the results of radiologists to deep learning models themselves, and the models outperformed them by a few percentages. It's very successful. This was a clinical implementation study, so it's very important. Another success was for breast cancer, and they determined breast density to correlate to tumors in breast. And they again compared the results radiologists have detecting breast density compared to the deep learning model, and it performed just as well and was very successful. And this is done by Dr. Lehman. She implemented this with another data scientist in her program, and they use this in their workflows right now, processing tons of breast screenings. And today I wanted to talk about a specific use case called lung lesion detection, which you've heard of, that I know a few radiologists have talked about, where it's false flagging a lot of nodules. It's a two-step process where they're detecting nodules that are possibly tumors or malignant tumors inside lungs, and then they detect it, and then they have to classify it whether it's malignant or benign. And this challenge actually started back in 2015 with a small data set, and then grew into the Luna data set in 2016. And finally, a kind of climax in 2017, where they offered $1 million prize to data scientists to develop a solution to detect lung cancer. And kind of going to talk about that technology today. So essentially, where we begin with processing CT scans or lung scans is that we need to take the DICOM data, its pixel data, and convert it into data structures that machine learning models can use, known as numpy arrays. And to normalize our data, because as you know as radiologists, that one patient to another, their pixel data is essentially not the same. We use Houston field units to kind of normalize the data set. So from there on out, we resample that data and we pass it into numpy arrays, and then we feed it into the detection models that kind of utilize a lot of GPU resources. Let's talk about the CT scan itself. A CT scan can contain over like 200 images to 250 images. One scan by itself, due to its width and length, is 512 by 512 pixels. That's a lot of data. That's over 200,000 data points possibly for a single image. And that can be a lot for machine learning itself. But when you have over 250 images on top of that, our data points go into the millions that need to be processed. And it's also compounded by the fact that this is 3D data. It's not JPEG, it's not PNG. A lot of quality machine learning models are in a 2D processing environment pretty much. They're only processing images simply on X and Y. But when we get into a 3D kind of place, processing time kind of shoots up. So let's say we take that lung scan and we plot it on a histogram. A majority of that data is actually air and leans in negative thousands on the HUs. So the next idea is simply like, okay, if I'm detecting for tumors in lungs, I want to look inside the lungs where the tissue is. So that's kind of where the 0 mark is on the graph. And they use a technique called segmentation. Essentially, segmentation is just an idea where we take a group of pixels and remove them from the image or kind of nullify them in the data so it's not really processed, it's not really of concern. They use a lot of thresholding techniques where you set a value determining whether or not one set of pixels lower than that value is white or greater than that value is black. So let's say all my air inside the lungs or outside of it is white and all the tissues are black. That's a thresholding technique, and that's very common. There's also, they call it binarization, so binary, black and white, or they call it watershed. The technique that we use is k-means. And the reason why there's different techniques for different models is that we want to retain the information within the data and not lose maybe anything important like the quality or the resolution. So essentially what k-means does is that it generates this lower right image called color labels. And in the next image, I'm going to use a metaphor to explain how the algorithm kind of works. It's fairly complicated, but not that bad. K-means, what it's essentially doing is that it's looking at its value, its HU value. You know, it's looking at the color of like let's say M&Ms. You know, this is green, this is red, and this is orange. Well, it takes that data point and averages that distance between each of the data point, what they call centroids. The simplest way I can explain it is that you're sorting M&Ms into different color groups, like that color image I showed you, and it can distinguish different labels. So what it did for us is that, you know, the inside of the lungs are their own label group, and then the background, the air, the blue and the yellow here, are completely separated out. And we just selected for the interior of the tissue. So what k-means did is that it does that for every single image in about 5 to 10 seconds, depending on how the code's written and the resources you have. So it's pretty fast, and it can get faster. So, you know, if you're getting hundreds of patients a day, you need to break down the data. And, you know, it might be kind of weird saying like, okay, we need to remove air data. Don't you want all the data? Not essentially. The reason why we segmented data is because the machine learning models themselves, the CNNs, have limited input. 3D UNet is very popular for doing segmentation itself, but it's also very time consuming. And essentially, its inputs for successfully detecting tumors, these guys were the winners. GRT won first place, and then Julian DeWitt and Daniel Hammerk won second place. The input size of the image are 120 by 128 by 128. And what that essentially means is that if my image is 512 by 512, it's not fitting into this model. It's going to slow it down, it's too much data, and you're not really looking where the tumor is. Like, you're processing air data, and the probability of knowing that the tumor is not there is really high. And you're feeding the machine learning, you're training it to do probably something very unnecessary in that point. So these guys figured out that, you know what, yeah, let's not process all the data, let's cut it down to inside of it, inside the lungs. So we finally have our lung image, and what we're doing here is that we're randomly cropping across the lung scan. And they build this kind of chunk of data called patch-based input, which is a collection of 3D arrays with more dimensions on top of that, fourth and fifth, that kind of include channel IDs and things like that. And essentially what is happening is that 128 is kind of like a Rubik's Cube processing through this 3D array. And it's augmenting, flipping, dividing, multiplication, generating what's known as features or multi-scaled values on top that the machine learning algorithm will learn about new values that kind of help it determine, like, why is there going to be a tumor in this 3D space or not? And it's all for probability. So when we finally get to the end of the process, I skipped many steps. This is a very simplified explanation, I'll say that. But what it's paying attention to in the data, what it cares about, is that we're looking inside this box. And it gets a box. And the machine learning goes, okay, is there a tumor inside of it or not? And what do I need to know? And it looks at nodule size, the volume of the nodule. It looks at its location. It looks at the density. If one nodule is calcified, its density is a little different. So it kind of puts it across on a binary cross empathy, where it's kind of saying, okay, if enough of these values on this side exist, it's not a nodule. If enough exists on this side, it's going to be a nodule. I would say that's a very simplistic explanation of it, but that's what it's kind of doing in this metaphor. The results that we get is known as bounding boxes or anchor boxes that are generated on top of the image. And that bounding box just kind of, in a sense, crops that data out and gives me important information like where is it located and what its size is. So you don't need to spend 15 minutes looking for a tumor. You spent milliseconds when you have thousands of patients. This process can get more complicated. Like we detected the tumor, but you want to know whether or not it's malignant is a question. So that goes into classification, and that goes into a more complicated set of algorithms. But this is a basic, data pipeline or workflow example of how these deep learning technologies kind of work. So the reason why we're here is that we want to do we have a summary of the reason why we're kind of here essentially is that we network with Penn State, and we talk to data science students, and we have access to the supercomputer at Penn State, and we have really motivated students who interact with a lot of data sets, and their goal is to really implement into a real IT system we're setting. So yeah, like I said already, we have this value, this motivation to understand what it takes to quality test software and code and document all that for you, so you can have a peek into what's going on into algorithms themselves. And what you have is real life experience. Things that work perfectly in a research model doesn't work perfectly in real life. Your CT data is extremely different from the data that is provided on these public data sets or even private data sets. One algorithm developed in, let's say, the University of Pittsburgh, it might not work at Penn State. So it's really important to get a solid understanding on how your data works and how to deal with its variability. And I think residents are looking for research opportunities and looking to mentor students and educate them on their world. So yeah, that's it. Thank you very much. Thank you, Dr. Shin, for inviting me. And yeah, if you have any questions, I'll take them now, or you can contact us at openvessel.org. So yeah, thank you. All right, so it's over, guys. Yeah, it's over. Okay. All right, that was fun.